Okay, let's continue with section 4.4 by looking at a very special type of exponential function called the logistic function. Okay, the logistic function. A common phenomenon in nature when considering population growth is that the population will start growing slowly at first, then more rapidly, and then it gradually levels off. And this makes a lot of sense because the population really just can't grow all the way to infinity. There's finite resources and finite land and all of that kind of thing. So you can't have a population going all the way up to infinity. It gradually has to level off. Okay, so this growth can be approximated by a mathematical model known as the logistic function. And so here it is, g of t equals m divided by 1 plus m over g naught. And yeah, we say the g with a little subscript 0 as g naught minus 1 times e to the negative kmt. And yeah, that's a big, weird, crazy looking function. So let's break down what all of these variables mean. G naught is the initial population. M is the maximum possible size of the population, and that's often also called the carrying capacity. K is a positive constant that's different for each model, and G of t is the population at time t. Okay, so lots of pieces involved here, and definitely when we start looking at some applications, it becomes a fairly complicated type of problem. Okay, but very, very fascinating, and these show up all the time when doing population models. So for this example, it takes a little while. We're going to find a logistic function, and then we're going to find a rate of change. And so this takes a while. I'll break it up into two separate videos. Okay, so here we go. Example 4. A species of rabbit is accidentally introduced to an island where it is not native. Uh-oh. So the initial number of rabbits is 8, and after 6 months, there are 90 rabbits. Okay, so suppose that the population of rabbits can be approximated with a logistic function where the maximum number of rabbits the island can support is 50,000. Okay, so again, finite amount of land, finite amount of food, whatever the reason is, 50,000 is the assumed maximum population the rabbits could ever reach. Okay, so let's find the equation for g of t. And I'm using a little note here that we're going to do exact values, not decimal approximations. A lot of times a decimal approximation will be okay, but depending on how you're asked to round, I don't want to get any rounding errors. And so if I use exact values, even though it's going to look a little bit crazy once we find that k value, we'll be able to round our answers like perfectly. Okay, so I don't want to do any rounding too early because that can throw off your answer by a factor of 10 or more. Okay, so I'm going to specifically use exact values. It just means it's going to look a little bit crazy, but I want to go ahead and use one of the more complicated types of examples in the lecture. Okay, and another reason why this is a little bit complicated is all through this process or all through this information here, they told us a lot of pieces of information, but they never told us k. And that's going to be the hardest part in finding the equation for the function. They didn't tell us that k constant. Okay, and that's going to be the hard part. Sometimes on these problems, you're actually given the k constant, and then it's not so bad. Okay, so let's get started. We're going to say that the g of t function equals. Okay, so I want to write down all the pieces of information that they gave us. So based on the logistic function here, we need m, which is the maximum possible size of the population. So I'll keep note of some of the stuff that they gave us. They did give us the maximum possible population of the island is 50,000 rabbits. Okay, so they did tell us 50,000 for m. Okay, so we can start by writing that. I'm going to leave a little bit of space because it's going to be kind of big. Divided by, okay, what else did we need? 1 plus, and then it's m over g naught. Okay, 1 plus, and then m, which is 50,000 again, divided by g naught. Okay, g naught is the initial number of rabbits. So let's write that one down. We've got g naught equals 8. Okay, so that's going to go right there. Okay, continuing. Minus 1, and then times e to the negative kmt. So we have minus 1, and then it's times e to the negative k, which we don't know. M, they told us, so that's the 50,000. and then t is pretty much the variable of this function. Okay? So, like I said, the hardest part is to find that k if you're not given k in advance. Okay, so in order to find k, what we want to do is we want to use the other piece of information. This gives us a point that we can plug in. So 6 months into it, so the units for t are going to be months. We know that the g of t function comes out 90. So we can write that as g of 6, and that will come out 90. This is what we can use now to find k. So let's make the function 90 equals, and then we're going to plug in 6 for t. But then as I write this down, I'm going to do a little bit more simplifying as I go. So as I'm working these problems out, I'll kind of do a lot of like speaking for how I'm doing some simplifying, maybe skipping a step or two here and there. So feel free to pause the video or rewind if you need more clarification. So here we go, that 50,000 in the numerator is going to stay put for a minute. Okay, divided by, we got 1 plus, and here's where I want to do a little bit of simplifying because this parentheses stuff, that's all just constant numbers that can be calculated. So definitely going to need our calculators for this entire problem. So let's go 50,000 divided by 8, and thank gosh, that's a whole number. So that's 6,250, and then minus 1 that's in there. So we can get, we don't need parentheses anymore, 6,249. Okay, so that's just the stuff from inside the parentheses. Then we have e to the, okay, so now remember we're plugging in 6 for t, and that's why this is all equal to 90. Okay, so if we plug in 6 for t, that's going to be 50,000 times 6, which is negative 300,000 because there's this negative in front. So let's write that as negative 300,000 K. All right, so we've got all the stuff plugged in there. We did some simplifying and we actually plugged in 6 for T. Okay, so make sure that's where this negative 300,000 came from. We plugged in T is 6 just now, okay? All right, so we have this equation now where K is the only variable. Remember, E is a number. So K is the variable we need to solve for, and that's the whole part of part A. That's the whole point here, okay? So let's solve for K now. We've got a big fraction mess, so definitely we want to clear fractions by multiplying by the denominator. So this entire denominator, we're going to multiply on both sides. So 1 plus 6249 e to the negative 300,000 k. And then on this side, I also want to multiply by that whole thing. 1 plus 6249 e to the negative 300,000 k. Okay, so this denominator will cancel with this thing. And then now I'm going to do my work kind of over here on the left-hand side to make sure that we've got some space. There should be enough space, but it's going to get a little bit crazier looking as we continue. Okay, so let's see right here. I don't actually want to distribute that 90 yet. Let's write it like this. Let's write it as 1 plus the 6249 e to the negative 300,000 k times 90 equals, and then so we cancel that whole denominator by multiplying both sides by that stuff, and so it's left with just 50,000. Okay, and then like I said, I didn't want to distribute that 90 in there because what we can do is we can actually divide both sides by the 90. Okay, so when we divide both sides by the 90, remember we're trying to get k by itself, so now I'm just kind of doing step by step to remove things from the k. So 50,000 divided by 90, let's see, that is not a whole number, and so all we can really do is reduce it. 50,000 divided by 90 would reduce to 5,000 over 9. Okay, so that's all we can really do right there. So let's write that down. Now we don't need the parentheses because we removed the multiply by 90. So we have 1 plus 6249 e to the negative 300,000 k. equals, and then yeah, this I'm gonna, like I said, I'm not gonna do any decimal approximations. I'm going to use exact values all the way through. So this is 5,000 over 9. Okay, just reduce it as much as I can. Okay, we want to get rid of all the stuff that's happening to the e, and so let's just kind of go step by step. So let's subtract 1 from both sides to get rid of that. And so yeah, step by step, 6249 e to the negative 300,000 k equals, okay, so 5,000 over 9 minus 1, maybe some scratch work. That's 5,000 over 9 minus 9 over 9, right? To subtract 1. So that's going to be 5,000 minus 9. So that's 4,991 over 9. Okay, with me so far? And that I don't think reduces. I'm just going to leave it like that. Okay, again, we want to get k by itself, so you want to get the e part by itself before we take the log of both sides. So let's divide both sides by the 6249. Okay, and when you're dividing a fraction by a fraction, it probably makes a little more sense to think about multiplying by the reciprocal. That's pretty much what it means to divide by a number, is you're multiplying both sides by the reciprocal. Okay, so that cancels here. And then we have e to the negative 300,000 k equals, and then this, again, I'm not sure if this is going to simplify or not, but the reason why I wrote it as like a fraction times a fraction is now we can see that it goes multiplying straight across. So we have the 4,991 on top, and then on bottom, calculator, 9 times 6249, and we get 56241. Okay, again, I'm purposefully doing it as precise as possible. Okay, now we've got the e part isolated, so here's where we want to take the natural log of both sides. So let's take the natural log of both sides, which allows us to bring the power down. But actually just remember that the natural log of e raised to a power is just the power. Okay, but again, that's because the natural log of e is 1. So bring down the power and then you multiply by 1, or the property just says that the natural log of e raised to a power just cancels out and you're left with only the power. So let's continue our work over here. That's specifically why we're choosing natural log, because it works really nicely with e. Okay, so then we have negative 300,000 k equals, and then we've got the natural log of this thing, the 4,991 over 56241. Okay, and yeah, so the ln e, remember the ln of e is just 1. I just wanted to clarify why we're using natural log, and then that power rule, everything works out really nicely when we take the natural log of both sides. Okay, so here we are. We're almost done with getting k. So divide both sides by negative 300,000. And this is going to look a little bit crazy, but I'm going to just write it like this. Negative 300,000, like so. And so we get k equals exactly the natural log of 4,991 over 56241 all over negative 300,000. All right. So that is k. If we did some rounding, or if you type that all into your calculator, you could get a decimal approximation, but I'm purposefully leaving it exact. Okay, we're not quite done because we want the equation for g. So what we want to do is take that k value that we just found, and we need to plug it in. We need to take this k value now and plug it in to our original setup. and then we have our answer for the g function. Okay, so note that the plug-in part is happening as that negative k times 50,000 t. So maybe just do some scratch here. What is negative k 50,000 t? Okay, well that's going to equal, so this is like my scratch work here. That's going to equal, so here's the k thing, so it's going to be negative ln 4991 over 56241 over negative 300,000, so that's the whole k number, okay, times the 50,000 t. Okay, so I'm just trying to find out what the overall exponent is going to look like for the e number once we plug this all back into the function. Okay, we can do a little bit of simplifying here because the 50,000 here is on top and the negative 300,000 is on bottom. And actually we do have negative over negative right there. So that's going to turn into a positive. Okay, so we have natural log of 4991 divided by 56241. Okay, and then 50,000 over 300,000. So you can type that in, or it looks like it's going to reduce to 1/6. So 50,000 divided by 300,000. And yeah, that reduces to 1/6. So I'm going to go ahead and write it like right here, where it's like divide by 6 now. And then there's the t. Okay, so that was my scratch work just to find out what the exponent on the e looks like. Okay, so we're actually ready to write our answer now. We have g of t equals, so the numerator is 50,000, so we're going to write that 50,000 divided by, okay, so I want to do the cleaned up version a little bit, so I started canceling out to show my work there, but we have 1 plus, and then that stuff in the parentheses, remember, was 6249. So we can use that. 1 plus 6249 e raised to the power of, and now it's negative 300,000 times k. All right, and so actually, yeah, so I was doing this part for the scratch work, but anyways, I already worked it out. And so we have that negative k times the 50,000. Oh yeah, the negative 300,000 was specifically coming from when we plugged in 6. Okay, so yeah, we have to use this part to do the scratch work. So we did it correctly over there. Okay, this is the general form where t is just t. It's not a number right now. It's just a variable. Yes, okay. So e is now raised to this weird thing. So this is e to the, and it's going to look a little bit crazy, natural log of 4991 over 56241. This is all over 6. And that is all an exponent on the e. Whew. All right, so like I said, that k number, a lot of times you might just be given the k number as a decimal, or you might round that k number at some point. But hey, this work to find the k number, I mean, it's really putting all of our algebraic skills to test here. Okay, and then definitely I wanted to do a little bit of scratch work to find out what is this exponent here on the e going to be once we actually plugged in the k number that we had to work out to solve. Okay, so there is the equation for the logistic function. Okay, like I said, takes a little while, so I'm going to make a separate video to pick up on part B. So stick around for the finale.